All right. Well, hello, chemists, and welcome again to another Sunday afternoon chemistry help session. Okay. So on this one, chemists, what I wanted to do is continue our chat on benzene rings. All right. There's my dog in the background. Bless, she just came up to see what's going on. At the time of this recording, it's snowing inside London. So yeah, it's going to be kind of an interesting afternoon, I guess. Take it down to the park, you can play with the snow. But anyway, chemist, here we go then. What I wanted to do was I wanted to continue our discussion of benzene chemistry. And specifically what I want to do today was a couple of things. Is number one, I wanted to talk to you about the physical properties of benzene. And specifically, I wanted to talk about the solubility and the boiling point of benzene. Number one, it's kind of like being like a newscaster, right? You know that newscaster guy that he was talking and the baby came in the background. Things like BBC News. It's me. As soon as I do a live chat, she comes up to see what's going on. But anyway, I wanted to do the physical properties of benzene, and I want to look at the melting point and the solubility of benzene and compare it to cyclohexane. This is an A-star question, all right, number one. And then number two is I wanted to talk to you about Friedel Crafts acylation reactions. And so to head this off, I wanted to chat about what I would call, well, I learned my chemistry 37 years ago, so I would call it ortho meta para directors. You younger chemists would know it as 1, 2, 1, 3, and 1, 4 directors. So basically, I want to explain what that is. And the reason I want to explain what that is because on the exam, what they tend to do is say, this is a product, you know, this is the reaction of the acylation, and then write down the product. And they always ask a question of what's the other product that could be involved? What's the other isomer that could be involved? So I wanted to go talk about that. And then we'll have a look at Friedel Crafts acylation reactions, and we'll take a look at acylation reactions with acid chlorides and acylation reactions with acid anhydrides. Okay, so this is a plan for today's lesson. Now, having said that, chemists, as you may have noticed the last couple of weeks, had a bit of a problem with the ink sticking on the page. All right, so I've been working with our good friends at Microsoft there, and unfortunately haven't come up with a resolution as to why the ink is not sticking on the page in OneNote. All right, and then I moved over to trying to use some PowerPoint, and that seems to work for a couple of minutes, and then it gets a bit sluggish. The pen gets a bit sluggish. And so I'm going to use something called Bit Paper. All right, our good friends at Bit Paper there said, try Bit Paper. And so here we are. It's an online writing, it's an online digital whiteboard. Maybe it'll work, maybe it won't. I tell you what, we'll give it a shot. Okay, so having said that, chemists, what I'm going to do then is I'm going to share my screen like this, and hopefully, let's see if the ink is going to stick on this one. All right then, so the thing I need to do is I do need to move my video link out the way a little bit there so I can see what's going on. All right then, so here we are then, chemists. All right, in black, right. And so what we're talking about is, pen, there we are. Right, look, we're looking at the physical properties of benzene. And this one, all right, it seems to be a fairly innocuous one. To do anything, yeah, okay, melting, melting point, solubility, boiling point, okay, easy. It is, but there's a little twist to it, okay, so a little deep dive at the end. All right then, so if I take a look at some data here, all right, so looking at my notes here, it's kind of weird. My notes are in OneNote, but I can write on OneNote and live stream at the same time. So if I take a look then at the boiling point and the melting point, okay, what I noticed that this is benzene, like this, okay. Now, do you notice how I'm drawing the resonance structures by using a circle here, okay? What I'm not doing, avoid the cacule structure, because if you start doing the cacule structure, then you start going down the path of, well, does the examiner think that you're talking about a double bond being inside benzene? And we all know that they're not double bonds inside benzene. We covered this last week. They're actually conjugated pi bond systems. Okay, so I always do this one and not this. Okay, don't do this, because otherwise, like I said, you kind of open the door to, well, are you talking about double bonds or what? No, you're not. You're talking about conjugated pi bond systems. But here we are. So here we are then. The boiling point of this one is the benzene is 353 kelvins, and the melting point is coming in at 279 kelvins, like this. And what they're going to compare it to directly is they then say, well, this is a one for cyclohexane, like this. All right, and the boiling point of this is 354 kelvins, and the melting point is 178 kelvins. All right, so having said that, pillow, okay, hold on. Yeah, this is like the one-day chemist. I thought, oh, I've been running every day, I think, since like the first week of January, and I thought today, oh, I'll go for a run later after my live stream at noon, and it's a bit cold out, and unfortunately then decided to snow, so I have to go running in the snow. I'll let you know how that goes next week, okay? But anyway, here we are. So this one, here's benzene on the left, and here's cyclohexane on the right. Benzene versus cyclohexane, and what they want to know quite simply is, why is the boiling point similar, number one, and why is the melting point totally different? Okay, so what you want to do then, chemists, is you want to recall what we talked about last week. All right, and it was this: is when you draw the benzene structure like this, and I will put in the pi sigma pi bonds. I'm going to label this as being right, pi bond and sigma bond, like this. All right. Then what you've done is you've made this essentially a really, well, it's a flat molecule. Now, the reason why it's a flat molecule, I think we went over last time, but here we go, is this one, is that if I expand this out even more, all right, so that you can see all the carbons and the hydrogens. Now, again, these aren't supposed to be double bonds. These are pi bond systems, but just wants to go look at this one here. You see this one, see this carbon here in red, all right, is this carbon here is sp2 hybridized. Okay, because remember the sp2 hybridization is only based on sigma bonds. All right, so the pi bonds are not part of the hybridization because we talked about this last week. This is the pi bonds are coming in from the unhybridized p orbital, right? So if I look at the sp2 hybridization here, right, and I put in blue, we put in blue the unhybridized p orbitals like this, then what you have, and I'll put them in like this, going on here and going like here, is what you have is the inability to rotate around the bond. And so we put down the benzene molecule, right? The benzene molecule is unable to rotate around a double bond. Actually, let me call this a conjugated pi bond system. So it is essentially, I go like this, my hands, right, my arms, it's essentially locked into place. The pi bond system here, all right, on the left-hand side here, the pi bond system there, all right, like my two arms, if you hold elbow to hand, right, it's locked into place. So it can't twist, it can't do anything except just be there because you can't break the pi bonds, which are the unhybridized p orbitals, which are above and below the sigma bonds. They're locked into place. So because of that, it is a flat molecule. All right. Now, this becomes important then because if I take a look at benzene here, and I compare it to cyclohexane over here, and when you study chemistry at university, you'll go into this, right? You get the boat and chair conformation. All right, and the boat and chair conformation, what they are is this. The cyclohexane, all right, looks like this. There aren't any pi bond systems, there aren't any double bonds, anything. And so my cyclohexane right here, if I take a look at this carbon right here, this carbon is just sp2 hybridized. And what this means is that they're all single bonds. So you can get rotation around the carbon, or I should say, you can get movement around the carbon-carbon or carbon-hydrogen bonds, right? So you can get movement around the carbon-carbon or the carbon-hydrogen bond. Right, this is not a flat molecule because you got this movement. And actually, you end up with two conformations, all right? Two ways this molecule can arrange itself, right? It's not flat like this. You actually get what's known as, this is the boat conformation. And this is your chair conformation. Right? You're thinking, well, yeah, okay, but what does this have to do then with the boiling point and the melting point. How to explain anything? Well, if I take a look then at, I'll do this in a pen color, right? Our friends at Bit Paper here seem to be onto a good idea because this board is actually fairly stable, right? So far, look, the reason why the boiling point and the boiling point are draw like this, you have similar boiling points, is because, right? Hold on a little bit better than that. You have broken all the IMFs between the molecules. Remember quality language a couple of weeks ago? Between the molecules. Now, we said last time that the IMFs present were van der Waals forces in benzene and the van der Waals forces in cyclohexane, right? Right. You've broken all the IMFs between the molecules, and so they're obviously in the gas phase, and so therefore they have the same boiling point. All right, similar boiling points. Okay, so you can write down you've broken all the IMFs between the molecules. Hold on. You have similar mass the molecule, and so therefore you have very similar boiling points, right? So the boiling point one was easy to explain, right? The one that's a little bit more tricky is the melting point. If you look at the melting point, you go, hold on a minute. Why is the melting point on this side 279? And why is the melting point on this side 178? Right. The reason is then, if you take a look at the way that the molecule is laid out, this one is flat, and this is the chair and boat conformation. So keep in mind, they both got van der Waals forces, right? It's the only IMF between the molecules. So if I take a look at right here, benzene, it's flat like this. Here is my other benzene like this. And so what you have is that you have a really, this is van der Waals between the two benzenes, right? You have really efficient packing into layers like this, which means that, and this is the bit that you got to be careful of, you're going to say there's more van der Waals forces, because as I tell my students, look, van der Waals forces are like chicken nuggets. They come in one size. There's more van der Waals forces. So the overall effect is that there's going to be stronger. So the overall effect is a stronger, I get stronger to be written a little bit more neatly there. Hold on. Is a stronger van der Waals force, all right? Right. So in other words, you've got because you've got really efficient packing on top of each other, right, the molecules on top of each other, you've got a really high surface area of contact between the two molecules, which means that you have more van der Waals forces. Therefore, the overall effect of van der Waals forces is amplified. Now, this is why the melting point is 279, right? Because you're thinking in the gas phase, the van der Waals forces, they were all broken. And so it really didn't have any impact on the boiling point. But when you come down to the melting point, the benzene's gone from the gas phase, it's in the liquid, and of course it's slowing down, right? It's cooling down. The molecules start to move around more and more slowly, which means that essentially what you get is that the molecules begin to settle down on top of each other, and you have layers and layers of benzene, which means that the melting point becomes higher due to the more efficient packing into layers. But on the other side, if I took a look at cyclohexane, all right, take a look at cyclohexane. Well, not the same thing, right? Because if I think like this is one, actually, yeah, I'll leave it like that. This is, move it down just a little bit. All right, trying to keep everything on the same page here, okay? So it's this bit, all right? Yeah, good enough. Right, look. You've got one cyclohexane molecule, say in the boat conformation, and then you've got the other cyclohexane molecule, say in the boat conformation like this. Well, you know from year 12 that in van der Waals, right, it's only the surface area contact. And so the only place that you can possibly have van der Waals forces is when the one molecule is touching, like here, you see like the two points, this boat conformation here, right? It's touching the other one. It's kind of like really, really close to it. So this is the only point you can have van der Waals forces. And so therefore, you can say that there's less surface area contact like this, which means that you have less van der Waals forces. Hold on, pen is just about to hang in there, chemist. Hold on. All right, I gotta admit it is a lot better than Microsoft's OneNote here. Larger, smaller surface area contact, therefore a smaller amount of van der Waals forces. Therefore, the boiling point is going to be lower, right? So this one here, chemist, this is the physical property of benzene, all right? So the boiling point is kind of easy to explain, and the melting point a little bit more tricky, because what you got to do is you've got to deal with the concept of chair and boat conformation for cyclohexane, all right? So this one is this bit. Now, hold on, just looking at my notes here really quickly. Okay, so what I wanted to do then is, oh yes, before we talk about Friedel-Crafts acylation reactions, okay, here we are on this bit. All right, now need to have a quick chat, conversation, if you would, about, we'll do this in black. All right. Ortho. And I write this a little better so you can read it. Look, ortho meta para directives, okay? Okay, so on this one then, here we are. All right, ortho meta para directives. All right, not in the textbook. and not on the spec, but it's just something which they include in the question and they kind of leave it as, well, like a cliffhanger, like why, you know, they just say, well, this happens. And you go, well, why does it happen? It's really simple. Look, all right, then I'll do one right now. All right, all it is this. If I take a benzene ring like this and I put a methyl group on it, right? So we did this when we were naming benzene compounds. We said that the naming of the compounds, they come from antiquity, right? And so this is known as methylbenzene. And it's one of the base compounds that we just have to learn. We're talking about nomenclature. Well, methyl, as in an alkyl group, all right, it favors the 1,2 position. So the methylbenzene, it favors the 1,2 position. Now, what I mean by that is this, is that if you then, and I'll do this reaction in a minute, Ken, we should, okay, look. If you then react it with an electrophile, which I'll talk about in a bit, okay, it's going to favor putting the electrophile on the second carbon. All right, that's what it does. So in university, you'll get into benzene rings in a bit more detail, all right, and do all the chemistry of benzene and resin structures. But for right now, just understand that if you do carbon 1, 2, 3, 4, and of course, because it's symmetrical on this side, it'll also be carbon 1, 2, 3, 4. It's going to favor putting the electrophile, in this case, the nitronium atom right there, the nitro right there, in carbon number 2. So this then would be known as, all right, and this one here is known as 1, 2 disubstituted, because you've got a substituent group on carbon number 1 and you've got a substituent group on carbon number 2, right? So this is the major product, right? The major product like this. Now, and this is the reason that I mention it, chemists, is because of this. They sometimes say in the question, and what's the other possible product? And you're left there wondering, I have no idea because it wasn't on the spec. It's not on the textbook. And you're just supposed to memorize what the other product is? Oh, no, let's not do that. Look. It can also, hold on, besides going in like the 1, 2 position, it can also go in the 1, 3. Like there isn't any reason why it can't go here. And trying to write this a little bit more neatly. So this is, hold on. This is my 1, 3 disubstituted. All right, disubstituted, which is a minor product. And you can also get it in the 1, 4 position. Is this electrophile? It could end up adding on to any portion of the ring. So it could end up down here. So this would be my 1, 4 disubstituted. And then can I squeeze that in down the bottom, I think, next line down. All right. Disubstituted. Which is a minor product. So what you need to understand then is this, is that the methyl, all right, is quite simply known as a ortho director. So right here in, we haven't used green yet today, right? This one here, look, the methyl is an ortho director. All right. It makes the electrophile favor the 1,2 position. So yeah, this one, the 1,2, this is known as, for us older chemists like me, this is known as the ortho. Hold on, try to write this a little bit neater. Right, not bad with the bit paper so far, I've got to admit. Right, this is my ortho right here. No, put it backwards. Hold on a second. Hold on. This is, that's right. Never mind. All right. Yeah, the 1,3 is my meta. I would know it as meta, the 1,3. And the 1,4 would be para. Okay. So the one that they tend to use then is methyl right here. Okay, which is a 1,2 director. And the other one, before we do the actual mechanism here, is your nitro, and your nitro group is a 1,4 director, okay? So the other one is the nitrobenzene. So start off with our base compound like this, right? This is nitrobenzene, which I'm trying to make him a little bit more neatly here. All right, this then is nitrobenzene. All right, and so nitrobenzene, it's a 1,4 director, it's a para director, and so if I do the same reaction, I got sulfuric acid here, and I've got some nitric acid added in with it. I'll talk about this in a minute. All right, it's going to make whatever you add onto it go in the 1,4 the 1,4 position. Okay, and so this would be 1,4 disubstituted, which is obviously the para, right? And this one is, it's your major product. All right. Now, what they will do, right? This is major like this. Right. What they will do is that they'll sometimes say, well, what's the other isomer? All right. And you just write down, well, you know, yeah, you could have it in the 1,3 position, or you could have it in the 1,2 position, okay? Now, oops, not methyl there. That's got to be nitro right here like this. Right, now then, like that. All right. So what I wanted to do then, before we get into the actual mechanism, is just talked about orthometallic para directors, okay? So when you see them on the exam, you're not surprised by what do they mean by other isomers. Why the other isomers? It's because the methyl group is an ortho director and the nitro group is a para director. These will give you the major products, okay? Now then, moving on, chemists. Let's go take a look then at a Friedel Crafts acylation. All right, and hold on, I want to start off with a nitration reaction here. All right then, so look at my notes. All right, the shame I can't get OneNote to be able to stream live. All right, but our friends at Microsoft haven't quite got that done yet, so got to keep moving on with what we've got. Okay, I have no idea what the issue is. So look, I think chemists, Friedel Crafts acylation then, right? So Friedel Crafts acylation. Now, it's broken down into 3 parts. Once you've done one, you've done every one of them, chemists, okay? All right, so the very first thing that I need to do is this bit. I need to, step 1, generate the electrophile. Hold on. Try to make that a little bit more. Need to generate the electrophile. Now, chemists, this is on your exam. It doesn't matter what exam board you're studying under. Look, this is on your exam for a point. Okay, now we'll do it with acid chlorides to begin with. All right, so here we are. They always, they're kind of, well, they're not too imaginative. Like they always tend to do ethanol chloride. Now, you may have noticed how I drew my methyl group here, right? Really, really careful for the exam board, showing that I know and that they know there's a bond between the carbon and the carbon. Don't do carbon, do like say CH3 and then put a bond going in, the carbon at the end of the hydrogen, because they'll mark it wrong, like we talked about last time, all right? It's got to be the bond to be very, very clearly drawn between the carbon and the carbon, please, on the methyl. And then what I'm going to react this with is some aluminum chloride there, like this. Now, what you understand is chlorine right here. This is a good leaving group. What does this mean? This means that the chlorine really wants to leave the ethanol chloride because it's got a very high electron negativity. In other words, it wants to take the electrons with it from the bond and leave the ethanol chloride. And they always tend to use ethanol chloride chemists, okay? Now, what you end up getting, if I turn this back into black ink, what you end up getting is this, is you end up getting the acyl ion, okay? So I've got to draw it like this. I'll try to be a little bit more neater than that. Hold on. Like this. Look, I've got to draw it like this. Okay. Because I wanted to show that I've taken the chloride out completely. Now, when I do that, I'm going to form, and I'll explain this bit in a minute, this. And you go, yeah, hold on a minute. Aluminum chloride, I thought it was AlCl3. How come you've got AlCl4 minus? Because All right, think back to when your teacher taught you about hybridization. All right, maybe they taught you about hybridization, but yeah, right. Aluminum is what? Neon 3s2 3p1. Now, question: is there room? Is there an empty atomic orbital? Yes. So if I get sidetracked for a minute, if I draw it like this, if I promote the electron here over to there, all right, and this becomes sp2 hybridized. All right, what I'm saying is I have an empty orbital right there where you can put in the lone pair coming in from the chlorine. And so this, if I draw this going over to here, this is my dative covalent bond. Like this. And I get AlCl4 minus. I explain like this because students want to know, well, why does the chlorine leave? Because it's very electron negative. And what's it going to do with the pair of electrons that it takes? It's going to donate them into the empty atomic orbital in aluminum. So even though it's sp2 hybridized, you have an empty p orbital right there. And so this becomes negative, and then this becomes positive. Now, having said that, what you've now got is you've now got your electrophile. Hold on. Come on, pen. Hold on. It's not bad, is it? You know, it's coming on. So this is my electrophile like this. Now, you're thinking, oh yeah. You know, when you did nucleophiles, you said that a nucleophile was a species has a negative charge or it's neutral, that has a lone pair on an electron negative atom that it can donate into. It can donate to form a covalent bond, right? You're thinking like hydroxide or water or ammonia, right? Or cyanide. Well, you know, from year 12, the electrophile is the dead opposite. The electrophile is it's a species with an electron deficient atom. It's a species with an electron deficient atom. Okay, hold on. Electron deficient atom. Right. Now, having said that then, the one, I make that a little bit more neater yet. The one that we're talking about then is the acyl ion. And you're thinking, yeah, it's kind of easy to keep straight in your mind because look, acyl ion, acylation, right. Now, step one then is generate electrophile. And once you've done these chemistries, you've done them all right. Step two, right here, is, well, the actual reaction. Now, this is the bit chemist. Once you understand that you've got the electrophile done, generated. Well, then here we are on this bit. Here is my benzene ring. Now, again, chemists always draw it like this. Don't do it using the Kekulé structure because, again, that kind of like leads you down the slippery path of, are you talking about double bond? No, you're not. Right, so it's this, and right here is my acyl ion like this. And with a positive on it. Now, one of the pi bond electrons is one of the pi bonds in the system here is attracted to this positive. So, you know, the two electrons in a pi bond, they are both attracted to this positive charge here. And so you end up getting this one like this. All right, now I'll draw it like this to begin with. Because the two electrons left and they joined a bond between the ring and the carbon, what's left is a positive charge right where you've stuck on the electrophile, in this case, the acyl ion. Now, you've broken the ring system, so you can't draw the ring complete like this. So it's kind of looking like this. And I'm going to put a hydrogen right here. Now, yes, there are hydrogens coming off the carbons going around, but what I wanted to do is emphasize this hydrogen here. Now, what happens is the hydrogen, and I'll explain why, collapses back down. The hydrogen gives its two electrons in the carbon-hydrogen bond back to the ring, and you end up forming this. You end up reforming the ring, and you've got this. Now, questions that students sometimes have is this one. Yeah, but why did the hydrogen decide to donate its two electrons? Like, you know, the carbon-hydrogen bond, just like donate its two electrons back in. And by the way, this is supposed to be, let me make this absolutely clear. You got to draw from the middle of the bond, chemists, okay? So yeah, you got to draw from the middle of the bond, please. Like this, middle of bond, back into the ring like this, yeah? All right, not from the hydrogen, middle of the bond, straight into the ring, right? Why do you reform the ring? Well, you know, last week we were talking about the ring stability. We had that diagram going, and we said that the benzene ring, compared to the theoretical model 135 cyclotriene, you know, the 135 triene, the benzene ring was, I think it's 152 kilojoules per mole more stable. And the reason for that, we said, is because of resonance stabilization. Same thing. You reform the ring. It's supposed to be ring. Hold on. You reform the ring. So that you lose some energy. So when you lose the resonance stabilization energy, right? It's more stable because you reform the ring. So right now it's like one of these high energy intermediates. You reform the ring and you drop down a little bit in energy, okay? And you form this. Now, on this one then, right. on this one, you did take off the hydrogen, right? And so I'm thinking I took off the hydrogen because, well, floating around, this is actually step 3. If I hit this button here, I should be able to scroll down a little bit. Can I? Maybe didn't like me doing that. Hold on. Let's not tempt fate on this one, is it? Right, so look, on this one here then. Can I do this? Yes, come on, a little bit more. Right, so look, on this one, chemist, what you've got is that you've got inside solution the AlCl4 minus ion that you made all the way up here. Okay, right, where did it go? Right there. So you're thinking, this is my catalyst. Our definition of a catalyst is something which lowers the activation energy of a reaction by providing an alternative pathway and is regenerated, it's not used up. And so one of the chlorides from AlCl4 is what picks up the hydrogen. And so in step 3, then, what you need to do is you need to regenerate the catalyst. Okay, and I'm going to regenerate the catalyst by saying this. Well, here is my AlCl4 ion floating around. I want to move this up a little bit. You can see what's going on. And here I am. Okay, it's going to pick up the hydrogen, right, from the benzene ring system there. And so you regenerate the catalyst AlCl3, and you make HCl. So this is the very last bit of the mechanism. Now, it did look to be a little bit of a intimidating mechanism, but it isn't, because you know what? It's the same thing all the time, chemists. You know, step 1, generate the electrophile. And the very first one, this is the one you just got to commit to memory. After you figured out what it is, you just commit to memory, right? Step 2 is the reaction. All right, you react it with the benzene ring. And then step 3 is when you regenerate the catalyst. Yeah? So this is the one with ethanol chloride. All right, now, the other one that they like to ask you about is the one with the acid anhydride. So hold on, I'm going to get some afternoon tea here. And my dog has come back up to say hello. All right, then, so here, right here, this is the one with the acid anhydride. Now, again, chemists, they're not really creative with these questions, you know, so the one that they're going to use all the time is ethanol chloride. Okay, like this. So we had, try it again. This is the ethanoic anhydride. Right, the previous one was ethanol chloride. So this is my ethanoic anhydride. So what it is this, is that, well, the very first thing I need to do is I need to generate anhydride. Well, step 1, same 3 steps, chemists. Look, step 1 is I need to generate the catalyst. Okay, so I got this. Here's my ethanol anhydride. And I'm going to use the same aluminum chloride catalyst, all right, as I did before. And the same idea applies. Look, this is my electronegative atom, my oxygen with my lone pairs on it. Yes, what's going to happen is that it's going to react with the aluminum. It's going to donate its lone pair of electrons to the aluminum, that empty unhybridized p orbital that we talked about there. And then you end up forming this. All right, so again, when I do it, oh look, what I've made is I've made my acyl ion like this. Like this. And now this is the tricky bit, right? You see this bit in orange. And this is what snapped off with the lone pair on. This is what snapped off with the oxygen when it left. And so I'm now just going to stick this onto right here. The aluminum chloride. Yeah. So last time we took off the chlorine as the electrophile, as the leaving group, and attached itself to the aluminum. This time I've taken off this bit in orange and I stuck it onto this. All right. So now what I've done then is I've generated my acyl ion like this, just like I did before. And then in step 2, right, is the actual reaction. But by now, chemists, I think you know what's going to happen. It's the same thing as before. All right, and I move my board up here. All right, it's this one. Look. Oh, this time let's do one with a nitro group on it. So look, we got this right here, because then it'll be the 1,4. All right, like this. And I'm going to react it with my acyl ion like this. I'm going to draw it like this, chemists, so that I've got the carbon with the positive on it facing in that direction, like this. 1, 2, 3, 4, and so it's going to come from here up to the positive on the carbon. I'm going to, now when you do this, Kim, you go put the arrow from the inside of the ring, not on the edge, on the inside of the ring like this, right? The examiner knows you're talking about breaking the pi bond system, okay? And so you end up with this. So I've broken the pi bond system like this. And in this case, I stuck the acyl ion down the bottom there. Where I broke it is going to be positive. Right. Like this. All right. And of course, I'll put my hydrogen on this side, because you know what's going to happen next, right? You know what's going to happen is I'm going to regenerate the catalyst. I'll do it in 2 steps. Middle of the bond, back into the ring system like this, indicating that I've closed the ring system like so. All right, and by reforming the ring system, I've lowered the energy, and because of that, it's more stable. And so I've got NO2 like this. And so you end up with this. Okay. And now this is the bit. Let me explain to you actually by doing it this way here. All right. This is a bit where on this bit, you have to have a little think about what you're doing, because it's not HCl that you form like you did with the ethanol chloride. This is step 3. You've got to regenerate the ring, the catalyst, regenerate the catalyst. All right. So what you've got then is you've got this. All right. From previously, I think I drew it the other way around in the notes up here. So hold on. Just let me. Yeah, we had this, right? We had CH3, C double bond O, and then, yeah, right, the oxygen. And we said the oxygen had bonded to the aluminum chloride like this. Right. Now this bit then is going to pick off the proton from the ring. And so can I just do this? Can I just, don't know if I can fit this in, AlCl3 like this. Right. What's going to happen is that the chlorine is going to be attracted, the other way around. Hold on. So what's going to happen is that put the lone pairs back on the oxygen like this, right? The oxygen is going to be attracted to the hydrogen donated electrons, and so you form the acid like this, and you regenerate the catalyst. Okay. So there you have it, chemists. So what we're looking at then is we've looked at in this lesson, we looked at the physical properties of benzene, specifically the one they're always going to ask you on, which is going to be the melting point of benzene, the boiling point and melting point of benzene as compared to cyclohexane. They're going over after the van der Waals forces between the molecules and the efficiency of packing the layers. All right, we did this one. A very light overview of ortho meta power directors. You would know them as 1, 2, 1, 3, 1, 4. And then we looked at some Friedel Crafts acylation reactions. The one with the acid anhydride and the other one with the acid chloride. So what I'm thinking is, I'm looking at the clock here, right? I'm thinking that next week, let's have a problem session, like a problem solving session. What we'll do is we'll do loads of questions, past paper questions, worked out examples, everything else, so we can lock in this bit of knowledge. All right. So on that note, it is still snowing inside London here. So don't know if I'm going running today, possibly take the dog for a walk, but you have a good rest of the afternoon. All right. And I will see you next time. All right. Take care.